In this video, I'm going to show you how to perform integration using substitution. So here's our first problem. We want to compute the integral of 3x squared times x cubed plus 1 all to the fifth power dx. So here's our first problem. We want to compute the integral of 3x squared times the quantity x cubed plus 1 raised to the fifth power. Of course, one way to compute this integral would be to expand out this x cubed plus 1 to the fifth power. If we multiply that all out and multiply the 3x squared also, then we'd get a long polynomial which we could integrate. But that's a lot of work. Really, there's a much easier way. First of all, notice that the derivative of this expression inside the parentheses appears elsewhere in the integral. The derivative of x cubed plus 1 is just 3x squared, which appears right over here. This is a good indication that we can use substitution. So we'll let this part be u, that is, u equals x cubed plus 1. Then if we take the derivative here, we have that du dx equals 3x squared, which means that du equals 3x squared dx. And that's exactly what we have right over here, 3x squared dx. For the sake of clarity, why don't we rewrite this integral once more, grouping the relevant terms together. So it's the integral of the quantity x cubed plus 1, and that's being raised to the fifth power, then that times 3x squared dx. So this here, the x cubed plus 1, that's u, and the 3x squared dx, that's du. So this is really just the integral of u to the fifth du. And we know that the integral of u to the fifth is just 1/6 times u to the sixth. And then we'll add our constant of integration, c. Lastly, to get our result in terms of x, we'll back substitute. We'll take that expression, u equals x cubed plus 1, and sub that in for u here. So 1/6 times x cubed plus 1 to the sixth, plus our constant of integration. And then we're done. We've solved it. That's all there is to it. Here's our next problem. We'd like to compute the integral of x cubed over x to the fourth plus 5. And we'd like to use substitution here as well. In particular, notice that the derivative of the denominator is almost equal to the numerator. That is, if u equals x to the fourth plus 5, then du dx equals 4x to the third, which is pretty close to that x to the third in the numerator. The only difference is that here we have a 4 that's multiplying the x cubed. But that's okay, since we're just off by a constant multiple, there's an easy fix for that. First of all, let's multiply by dx on both sides to get du equals 4x cubed dx. Now the thing here is we only have an x cubed times our dx, so we don't want that 4 there. And the easy fix is to just multiply both sides by 1/4. So we get 1/4 du equals x cubed dx, and that's what we can sub in for x cubed dx, just 1/4 du. So let's write this again very explicitly. We have this fraction 1 over x to the fourth plus 5, that's just the denominator part, and then the numerator was x cubed, and then we've got our dx. This part here is going to be u, and this part here is 1/4 du. So the integral becomes 1 over u times 1/4 du. Now to simplify this integral, we can move that 1/4 out in front. So 1/4 times the integral of 1 over u du. And the integral of 1 over u is just natural log. So we have 1/4 natural log of u plus our constant of integration. Finally, we just back substitute to get our answer totally in terms of x, we just back substitute. Bring in that x to the fourth plus 5 and sub it in for u. So 1/4 natural log of x to the fourth plus 5, the absolute value of all that, plus our constant of integration c. We're pretty much done. Just notice that we can simplify a little bit further, x to the fourth is non-negative because it's an even power of x, so this expression inside of the natural log is always going to be positive. As a result, we can remove the absolute value signs. So 1/4 natural log of x to the fourth plus 5 plus our constant. And there we go, we're done. Here's another example. We want to compute the integral of x over the square root of x squared plus 1. And you can probably infer that we're going to use substitution on this one. So we look for an expression along with its derivative in the integral. Or at least an expression whose derivative is very close to something else in the integral. If it differs by a scalar multiple, then we're okay. If it differs by a constant multiple, then that's okay. Do you see it? Take a look at that x squared plus 1 in the denominator. The derivative of that is just 2x, and x appears in the numerator. And 2x versus x, those just differ by a constant multiple, so we're okay. We'll let u equal x squared plus 1. That way, du dx is equal to 2x, which means du equals 2x dx, and we just want a single x dx, so we multiply both sides by a half to cancel out that 2. So 1/2 du equals x dx. So this x dx part there, that'll be our 1/2 du. We'll just write it out once more explicitly. So 1 over the square root of x squared plus 1 times x dx. We perform our u-substitution, and we get 1 over the square root of u times 1/2 du. And now we just simplify. So this 1/2 can be brought outside the integral. In particular, this 1 over root u can be written as u to the power of negative 1/2. The power of 1/2 gives the root, and the negative puts it in the denominator of a fraction. So u to the negative 1/2 times 1/2 du. And hey, that's an easy integral. That integral just evaluates to u to the positive 1/2. Of course, plus a arbitrary constant c. Now we can back substitute, get our answer in terms of x using u equals x squared plus 1. So this becomes x squared plus 1 to the power of 1/2 plus our constant. And though this isn't strictly necessary, let's just write this power as a root. So root of x squared plus 1 plus our constant. And then we're done. We've got it. So now we know how to perform integration using substitution. Not only does this let us solve integrals more quickly, but it also allows us to solve integrals that we wouldn't be able to solve otherwise, like this one here. In the future, we'll continue to get plenty of practice using substitution. It's one of the most powerful techniques for integration.